We've been asked to use the sixth partial sum to find an interval that contains the true value of the sum of the reciprocal squares, so the series from 1 to infinity of 1 over n squared. Well, in our last video, we learned an inequality that would give bounds for the remainder of a convergent series. As long as the nth term was a continuous function with positive decreasing values, well, 1 over x squared meets that requirement. And this is the inequality we get to use. Well, at the very end of that video, we discussed that the remainder could be thought of as the sum minus the nth partial sum, giving us this inequality. And then if we add s of n to each of the three pieces, we would actually get an interval for the true sum. So I need to calculate the sixth partial sum, because that's what I'm asked to do, and that will give me the s of n. And then I have two improper integrals to worry about to know what to add in the two places. Let's find that value of the sixth partial sum first, since that will be, I think, a very straightforward piece of this problem. So s sub 6 would be 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 plus 1 over 25 plus 1 over 36. The sum of the first six reciprocal squares. Well, off camera here, I'm just going to use my trusty TI-84 to help out. So I get about 1.49138888, and we could write that down as a 1.49138 repeating. My graphing calculator tells me that that is 5,369 out of 3,600. All right, so that is the sixth partial sum. Now I need to worry about this improper integral. So I'm actually going to think about this as an integral from some number a to infinity of 1 over x squared dx. Now I know that I'm supposed to be thinking from n to infinity and from n plus 1 to infinity, but I'm very, very lazy, and so I'm going to use an a down here, and after I've evaluated, I'll know I can let a equal n and then a equal n plus 1, and I'll have accomplished all of the work I need to do, hopefully working just a little less hard. So I'm going to rewrite this as limit as b approaches infinity, the integral from a to b of x to the minus second. All right, do a little substituting in here. B is still going off to infinity. A is a constant. I get a 1 over b plus a 1 over a, and that's just a 1 over a. So if n is my lower bound, just a 1 over n, if n plus 1 is my lower bound, that'd just be a 1 over n plus 1. So looking at this inequality, the true sum should be between this number, about 1.49138 repeating forever. I guess I didn't need to say the about if I'm going to do the repeating forever, plus 1 over n. Well, let's see, what's n for us? Well, it is 6, so plus 1/6, less than or equal to 1.49138 repeating, plus 1 over n plus 1. Well, n 6, that's 1/7. And that's going to give me my interval. So again, I'm going to run home to my calculator here and see. So I'm going to go 1.4913 9. I'm just going to go on and round to the 1, 2, 3, 4, 5th decimal place plus 1/7. 1.6324. I'm going to round to that 4th decimal place just because I feel like it. And then 1.49139 plus 1/6. 1.6581. The true value of the sum of the reciprocal squares has to be between these two numbers. Now, it's just nice to know that and by we, I mean, using the whole of mathematics, we could determine that this sum is actually pi squared over 6. And we see that value is between the two we have found here. If you wanted to find a single value to approximate s with, we could find the midpoint of this interval and use it. So add those two numbers, divide by 2, and I get 1.64525. By using the midpoint, I know that I'm off by no more than half of the distance between the two endpoints. And just looking at the value of pi squared over 6, that's not a bad approximation using this method, only going out to the 6th partial sum. Of course, if you want to make this approximation better, go out further in the partial sums, like use the 10th partial sum or the 20th, and you'd get a value that's even closer to what this is converging to.